So before I start my presentation, I do have a confession to make, and the confession is that these are not my first set of slides. I made my first set of slides, and I showed it to my friends, and I ended to the slides, and then the question was, why do we need this? So I realized my grave mistake, and I changed over my slides, and now for the rest of 10 to 12 minutes or so, I would be talking about why do I think that we need to combine ZK plus FHE to build really cool on-chain hidden information on-chain applications. So what are these games that I'm talking about? So these are hidden information games, and you can build them using, you can build hidden information games using ZK. But when you want to have a game where, or like for example auction, in which you have private state from multiple user, and you want to compute over private state from multiple users to have some global state, you need a combination of ZK plus FHE. FHE alone would not do. ZK alone would not do in that case. So first, what is FHE? Right? So FHE stands for fully homomorphic encryption. And the idea is pretty simple. You have your private data. You have a secret key, that golden secret key right there. And you encrypt your data using that secret key to produce a ciphertext. And then you hand it over to a server or to someone else. And that someone else can compute any function on top of that ciphertext so that the same function is computed on your data and gives you an output ciphertext. And you can take that ciphertext, decrypt it to find the function evaluated on your data. And that's pretty cool. So today I'll be talking about something called FHE Oracle. And the initial idea of this thing, I mean, most of the ideas of this FHE Oracle thing comes from Penumbra protocol and this paper by Wei Dai called Pesca. Instead of just jabbering over here, talking about theoretically you can build stuff and stuff, what I'm going to do is I'm going to motivate this thing using an example. So I'll be building a hidden information game, and the most famous one in blockchain is private auctions. So I'll be building private auctions in front of you guys. Okay, so the first thing that we need to build private auction is something called threshold FHE. Well, in general setting, the way FHE works is a two-party setting where you have a client and you have a server, and the client encrypts their data and gives it to the server. Server computes on top of that and gives you an output ciphertext, and you get it back. That's not interesting. What's interesting is threshold FHE, which we can use in decentralized setting. And the setting is that you have multiple nodes. So you have multiple nodes, and they can perform something special that we usually refer to as distributed key generation. And with distributed key generation, what they can do is that they can generate a master secret key, but in reality, that master secret key doesn't exist. What exists are these shards of the master secret key, S0, S1, S2, S3, S4. And then once they've done this, what they can eventually do is that they can collectively generate master public key, or they can collectively perform something called threshold decryption, which is counterpart of decryption in threshold setting. And another important thing to note is that unless a certain threshold of these nodes collude, your ciphertext is not revealed. So what is FHE Oracle? Well, FHE Oracle is this threshold FHE network, and that is it. So it can perform DKG, it can run FHE compute, and once you encrypt ciphertext using the master public key of this FHE Oracle, it can run FHE computations on top of it. And another key thing to note is that the FHE Oracle is stateless. I would also like to mention over here is that this threshold setting is somewhat less secure than having an n out of n setting. So you have this threshold assumption. So as long as, in case of auctions, I'm sort of building in threshold setting, but it could be that your application only is okay with n out of n setting, where every client holds the secret share. And that is much secure than this. But for now, let's stick to this. Okay, so the second thing that you need is a transparent layer 1, layer 2. And that's a blockchain. And since we are building hidden information games, we need a notion of a private state. We need a notion of we need a way to hide information. And the way we would be doing right now is that building a very vanilla state nullifier model inside a smart contract. So you have a private state, we have a state tree and a nullifier tree, and the user state is stored inside this tree. So in case of auctions, what you can imagine is that the user bridges themselves first to the smart contract, deposits their money, and then use their state inside the smart contract, inside this private state, to bid in different auctions. Also, another key thing to note is that if your thing was not transparent, like if it was a private layer 1, layer 2, like Aztec, it would not be this case. So you wouldn't have to do all this tooling to actually build this. You wouldn't need to, write the smart contract because they provide it by default. Okay, so let's run through the auction. So you have Bob the builder that wants to list an item for an auction, right? So they send a transaction to the smart contract and list an item for the auction. And then you have the FHE oracle. The FHE oracle runs distributed key generation and generates the master public key, right? And then makes it public, like everyone knows about it. And then we have Alice. Alice wants to bid 1 ETH. So what should Alice do? Well, Alice first creates 2 nodes. First is a transfer of 1 ETH from herself to Bob. That is the seller of the auction. And the second one is a 1 ETH transfer to herself. And then she makes necessary proofs for the nullifier. She nullifies 1 ETH from a state and makes necessary proofs. And then Alice would take the master public key of the FHE oracle, encrypt her bid, that is 1 ETH, using the master public key, and produce a bid ciphertext, and produce necessary proofs, proving that she has encrypted 1 ETH only as a bid ciphertext. And then she will take the necessary proofs, and she'll take her commitments to 2 nodes and send it to the smart contract. And then she'll take a bit ciphertext and send it to the FHE oracle. And then the smart contract receives all the proofs, verifies all the proofs, and then adds the 2 node commitments to a temporary buffer. And then let's say that Mickey the Mouse and all the degens of the world have placed their bids, and the auction ends. Wait, the auction should end. The auction ends, right? So what happens after that? Well, the FHE oracle has all the bit ciphertext. So what they do is that they collect all the bit ciphertext and compute on them on top of these ciphertext an FHE auction circuit, and produce a ciphertext that encrypts the identity of the winning bidder. And then they perform threshold decryption on the identity ciphertext to reveal the identity of the winning bidder and send it over to the smart contract. And then the smart contract receives the identity of the winning bidder. And for the winning bidder, the smart contract would take their commitment to Bob and add it to the state tree. So this is essentially a transfer of the winning amount to the state tree, and delete their self-transfer commitment. And for the rest of the losing bidders, it would take their commitments to themselves, like a self-transfer commitment, and add it to the state tree. And for the rest of them, it would delete. And the rest of the commitments for Bob would be deleted. And that's it. We're done with auction. So a lot of people say that FHE is too expensive. Yes, it is too expensive for certain cases, but if you're designing an application where you do not require a lot of latency and stuff, it is not that expensive, honestly. So I prototyped this FHE auction circuit out, which reveals the identity of the winning bidder only, and it does not take that long. So for example, for 128 bids, where each bid is has a precision of 64 bits, it takes 20 seconds on a machine with 16 cores. And as you put more cores to it, the time would decrease. And as you decrease the precision of the bits or increase the precision of bits, the time would decrease linearly or increase linearly. And that's it. So this is the link to the FHE auction circuit. You can scan it. And this is my contact if you want to contact me anytime. And I've got few things over here that you can ask questions, sort of suggestions that you can ask questions for. Otherwise, yeah, go ahead. That's it.
Why is Alice sending Bob ETH and then send back in the first step of this process?
you say that again, please? Oh, sorry.
You showed that Alice first is sending 1 ETH to Bob and then sending it back to herself and then.
Yes, so there were two commitments, right? And the two commitments, this is for actually when Alice wins, her commitment to herself would be deleted. Because Alice needs to transfer 1 ETH to Bob, so only the commitment to Bob would be added to the state tree. If she is the winner. Oh, Joe has a question. So did I answer your question correctly?
Can you explain, like on 5, how the FHE master public key is generated in this Oracle network?
Yes. So in a very general setting, the way it works is that there's a protocol called DKG, which is distributed key generation. It's an MPC protocol, and I think it's 1 round, and they send shares to each other, and that's it. After that, they can do the stuff that they want to do. But in this case, if you want active security, in the sense that like if you want to recognize who is sort of like cheated and stuff, the threshold is pretty low because it is around like n by 3 assumption. So yeah, it's like if you want active security, then things sort of mess up a bit.
I wanted to ask about ZK snarks represented with lattices. If that was implemented in practice, do you think that it would be more efficient versus a more efficient implementation versus using CirCom for this?
No. It's like ZK snarks with lattices is still a problem. Like it's still being explored. But I don't think it would be more efficient than anything what we have right now.
Gotcha.
For with elliptic curves. But you should ask someone much better than this on me. Yeah. Oh, this is very generic, so it's not like I've not instantiated with anything. So you can use any proof system for this. I would, if I were to use, I would simply use Helio2 for this. Writing, like, you just need to write proofs for like encryption and stuff, and I believe the next talk focuses on that. How to generate proof of encryption and proof of decryption for lattices, but yeah.
Okay, simple question. Do we trust FHE Oracle, or it has something like a proof?
No, it does not have a proof. You need to trust the threshold assumption.
Okay.
Which is why I mentioned that in n out of n setting, where each client holds the secret, it's much secure setting than having this. Okay. So if you're able to design games where each client holding a game. So for example, you're building a game and then they come online and do the stuff. That makes much more sense than this. But just to motivate this thing, I sort of went with this.